The scientific method is a systematic approach to research. It's a method for science to correct itself. When you look at a flowchart showing the steps of the scientific method, it looks all neat and tidy. But when you're a part of it, it can feel messy and convoluted. The Michelson-Morley Experiment is a famous failed experiment, but it still debunked a 2,000-plus-year-old hypothesis and led to some of the most significant breakthroughs in modern science. Let's dive into the history of this experiment and see how it demonstrates the power of the scientific method. The first step of the scientific method is to define the problem. Let's talk about waves. A wave isn't an object. It's a disturbance in a medium that propagates through space and time. Think of waves in water. The waves aren't the water, they're the movement of the water. In 1801, an English physician named Thomas Young showed that light acts as waves in his famous double slit experiment. He discovered interference effects of light, where when light passes through two slits, it gives a series of alternating dark and light bands. This is analogous to how waves travel in water. There are undulating peaks and troughs. So Young concluded that light acts as waves. The problem that a lot of scientists were trying to solve in the 19th century was, how does light move through space? What medium are light waves propagating through? The second step of the scientific method is to develop a hypothesis, or an initial explanation based on limited data. Way back in the 4th century BC, Aristotle described the aether as an element lighter than air that surrounds celestial bodies. Thinking in terms of the ancient Greek elements of earth, air, fire, and water, he was describing a fifth element. Then, after Thomas Young generated data that supported light acting as waves, the idea of the aether gained popularity. In 1818, Augustin Fresnel introduced the wave theory of light, proposing that light is a wave traveling in an ether. Fresnel was explaining the results of Young's double slit experiment by combining it with Aristotle's ether and Huygens' wave theory of light. The logic was this: if light acts as waves, waves are an energy traveling through a medium, and light can travel through space, it stands to reason that space can't be a vacuum. Space needs to be filled with something, some medium through which waves of light can propagate. The hypothesis was the ether. The ether is a weightless, transparent, and frictionless material. The ether permeates everything, everywhere, throughout the universe. The ether is some sort of elastic solid, meaning a solid that can go back to its original shape after being deformed. This category of solids also includes steel, rubber, and wood, but somehow the ether also just lets everything pass through it like it's not there. This idea of the ether didn't just newly resurface after 2,000 years. A century before Thomas Young, in 1704, Isaac Newton proposed the particle theory of light, saying that light is made up of a bunch of tiny particles. This theory explained the geometric nature of reflection and refraction of light, because particles can travel in straight lines and bounce off of things at predictable angles, just like light. And particles don't need a medium to travel through space like waves, but there's still a problem for Newton to explain. The problem with the particle theory of light is that if light is made up of particles, it doesn't explain diffraction, or the bending of light around the corners of an obstacle or through an aperture. With diffraction, light hits a region that geometry says should be in the shadow. So Newton literally added a fudge factor to his calculations, saying that an ethereal medium is responsible for diffraction. Newton was such a brilliant scientist, inventing calculus and giving us laws for gravity and optics, that Newton saying something was true was enough for most people to believe it. But do you realize what just happened? Newton and Fresnel have competing theories about if light is made of particles or waves, but they agreed on the existence of the ether. Everyone thought that the ether was a real thing. If a hypothesis survives many, many experimental tests of its validity, it can become a theory. A theory is a unifying principle that explains facts and/or the laws based on them. And scientists are in agreement at this point in time that the ether is real. Maybe they don't have all the details worked out about how light travels through it, but its existence was used to explain a lot of scientific observations. The third step of the scientific method is to perform experiments. In 1879, James Clerk Maxwell suggested that the velocity of Earth in the ether may make the ether optically detectable. He had calculated the speed of light and realized how it could be used to detect the ether. Think of it this way. Drop a rock into water and a wave spreads out. Let's say the speed of that wave is 1 meter per second. If you're on a boat and that boat is not moving, you will see the waves pass at a speed of 1 meter per second. But what if your boat is moving? Let's say you're heading into the waves at 10 meters per second. The waves would approach you at 11 meters per second, the combined speed of you and the waves. If you were instead going the other direction at the same speed, you would be going faster than the waves and overtaking them at 9 meters per second. You can calculate your speed relative to the waves in the water. Instead of being on a boat moving through waves in water, we're on Earth moving through light waves in the ether. But the same logic should apply. We should be able to measure Earth's speed relative to the ether by measuring the speed of light in different directions. This is what Albert Michelson and Edward Morley were trying to do. This is the problem they were trying to solve. They were measuring the speed of light in different directions so that they could calculate Earth's speed relative to the ether. Their hypothesis, in simple terms, was that light traveling in the same direction as Earth should have its speed increased by that of the Earth. For their experiment, they split the beam of light into two and sent the two beams into perpendicular directions. Using mirrors, they reflected the beams back to the starting point. Because the beams had traveled the same distance but perpendicular to each other, they should be affected differently by the ether and would return to their starting points at different times. The fourth step of the scientific method is to contribute to the body of knowledge, which Michelson and Morley definitely did. But the result of their experiment was not what was expected. They found the speed of light to be the same in different directions. Their hypothesis was just flat out wrong. The Michelson-Morley experiment is called a failed experiment because their hypothesis was wrong. They still contributed knowledge. Even a null result or an unexpected result is knowledge. Michelson described the result as the hypothesis of a stationary ether is erroneous. There is no ether. This experiment disproved what scientists all agreed upon. The knowledge that this generated paved the way for Einstein's theory of relativity, de Broglie's wave-particle duality of light, and quantum mechanics. The path through the scientific method isn't always smooth. We don't always get things right on our first try. Sometimes it takes centuries. The next time you fail, I hope you fail as spectacularly as Michelson and Morley. Next up. If you have any questions, feel free to leave a comment down below. Thanks for watching Chemistry in a Nutshell. If you feel that I've earned it, please like this video and subscribe to my channel.